recording. Okay. So what we are going to do now, today, is finish basically very, very sketchy and brief introduction to spectral geometry of modular surface. It's a huge subject, and we cannot just, you have to teach a course completely on its own. So I'll just, so this is spectral geometry. This modular surface. I mean, very brief, even sketch, or I can't say. It's a very brief sketch, I would say. So it's almost, I would say almost nothing, I will say, except I will report on some results, and that's all. Because it takes time to develop all the technology. So let's recall. So we have this Poincare upper half plane. Y positive. So we have this metric here. Yeah, so we have this Riemannian metric here, ds squared equal to dx squared plus dy squared over y2. So this is a metric of constant curvature -1. So constant, that's very important. Curvature A equal to -1. So this is also known as hyperbolic plane. Because it's the model of non-Euclidean geometry that's here, hyperbolic plane. As I said, this is a unique two-dimensional, simply connected, complete Riemannian manifold, constant curvature. So to unique up to isometry. Simply connected. And connected. Maybe I should say that also, I don't know. Maybe connected is included in simply connected, I'm not sure. Simply connected, complete. Complete means that geodesics can be continued from -infinity to infinity. They don't stop at finite time. I.e., each geodesic extends to well, -infinity. I mean, if you want to see a non-complete Riemannian manifold, it's very easy. Just take the plane and cut out something from the plane. You get a non-complete space. You see, what I'm saying is that, I mean, here is non-complete. If you want to, it's very easy to construct a lot of surfaces that have constant curvature, which are simply connected, have constant curvature -1, but they are not complete. I mean, if you want to construct a non-complete, Riemannian manifold, just take R2, for example, -R. I mean, So you just take R2 with the usual metric, so the geodesic that starts here, I mean, in this direction, only goes so far, because you reach the boundary, you cannot continue. And in this direction, you can continue, in this direction, you cannot continue. So this issue of completeness is quite crucial. So this was another side remark. This is another side remark. So what is the statement? The unique optoisometry, simply connected, complete Riemannian manifold of constant, Riemannian surface, two-dimensional, of constant curvature. Equal to -1. So, what is the importance of this hyperbolic space for Riemannian geometry? What is the importance of hyperbolic space for Riemannian geometry? So its importance, let me make a comment because that's relevant for us. Its importance for surface theory, for Riemann surface theory is this. Is the following. There is a very famous theorem called Uniformization Theorem. Let me recall the Uniformization Theorem. This is a theorem due to Poincaré and Kobe. Although, there was some preliminary work by Klein and other mathematicians in the 19th century, but they proved it around 1907. Two independent proofs were given. What is this uniformization theorem? It says that any two-dimensional Riemannian manifold, its metric can be conformally perturbed to turn it into a constant curvature metric. For any mg, dimension of m equals to 2, there exists a unique conformal perturbation, conformally equivalent, I would say. I guess we can see it here too, conformally equivalent metric, G tilde equal to e to the h g, such that this new metric has constant curvature either 1, 0, or -1, such that curvature of G tilde is equal to either 1 or 0 or -1. Okay, so this is so what happens in each case? Well, to decide what's the whether it's 1 or 0 or -1, this depends on the genus of the set. In the compact case, compact means closed, closed without boundary, compact without boundary case. There is this theorem, which is Gauss-Bonnet theorem. Gauss-Bonnet says that if you integrate over the curvature of any metric, right, with respect to the volume form over this manifold M, you always get, if you divide by 1 over 2 pi, you always get Euler characteristic of the surface. Okay, so this Euler characteristic is either 2 or 0 or is negative. Okay, so let me write it here. Chi G chi M equal to 2 minus 2g. So for g equal to 0, chi m is a positive number, is 2. For g equal to 1, so this is a sphere. Topologically, a sphere g equal to 1, chi m is equal to 0. This is torus, topologically again. You're not talking about metric, you're just talking about topology here, right? And for g bigger than or equal to 2, chi m is less than 0, is negative. Okay, so the majority of cases is actually covered by this situation where Euler characteristic is negative. Right? And in that case, then the constant curvature has to be -1, because if it's 1, then we get positive. So in this case, so this is the case that we are looking at. So in this case, k d tilde is equal to 1. That's the only possibility. So it follows from this uniformization theorem that all genus surfaces of genus bigger than or equal to 2 admit a Riemannian metric of constant curvature -1. Okay, so let me write it. Uniformization theorem implies that any surface, any closed, smooth, I should say oriented surface admits a metric of curvature, constant curvature, k equal to -1. So this is always the case. Okay, so we have this surface like this. There exists such a metric on it. Okay, so let's look at the universal cover of this surface. Okay, then it's universal cover. Universal cover. So if you look at universal cover of this surface and tilde, the universal cover again is a Riemannian surface with a metric of constant curvature -1 and is simply connected. Okay, so this is Riemannian surface of constant curvature -1, which is simply connected because it's universal cover. And completeness, I believe, it follows from some generalities also. So then it follows that M tilde is upper half plane. So tilde, by the result that I mentioned at the beginning, that this H is the unique, complete, simply connected space of constant curvature -1 Riemannian. So this M tilde must be isometrically isomorphic to H. So what does that mean? It means that any surface of genus G bigger than or equal to 2 is going to be a quotient of H by some subgroup of isometries. Okay? So the nice result now is the following, is that any genus G bigger than or equal to 2 surface is a quotient gamma. So what is gamma now? Well, this gamma, of course, is a fundamental group of the surface. That's why we know in general this has to be the fundamental group of the surface. So this gamma equal to pi 1 of m, which is pi 1 of the surface of genus G. But this, in algebraic topology, you compute this pi 1 of such spaces. That's exactly the group generated by, so gamma is the group generated by 2G generators. So you just choose pass around each hole in this direction and another one that direction. One thing around this direction, the other one the other direction. Well, you have to, so I will draw a better picture soon. So gamma is generated by A1, AG, B1, BG, 2G generators that satisfy one relation, namely product of commutator of AG, BG is equal to 1. AI, BI, sorry. Equal to 1, I from 1 to G, and this commutator, of course, is the group commutator, means AI, BI, AI inverse. So these are one relation. So the group, this fundamental group, has a presentation with one with 2G generators and one relation, which is this one. Okay, so this gamma now is a subgroup of group of isometries of an orientation preserving isometries of this upper half plane, right? But that group, we know what it is. This is subgroup of isometries of upper half plane. But this group is exactly PSL2R. No, it's yeah, PSL2R, yeah. So the conclusion that we arrive at is that by looking at discrete subgroups of isometries of this upper half plane, we can construct all Riemann surfaces. Actually, I mean, constant curvature Riemann surfaces like that. Now, the converse is not true. It's not true that if you take any discrete subgroup, so this is discrete, but the converse is not true that if you take any discrete subgroup of this, the quotient is going to be a smooth manifold, because that group may have torsion, may have non-trivial isometry groups, and so there are conditions on gamma in general. This is known in general for which groups the quotient is going to be smooth, and for which groups the quotient is smooth and compact. So conditions are known completely for this. So this is one importance of hyperbolic geometry for this whole theory of Riemannian surfaces, which because we can construct all of them like this. The case that we looked at, actually, it's not this, unfortunately, because we have a subgroup that does not. I mean, the action of gamma on H is free, right? So this, by definition, because this is a covering map. So the action of the fundamental group, I mean, it's a free action. So this is a free action. The case that we looked at, started looking at, is not covered by this. We have a non-free action. Okay, so that's something that we have to be careful. So this was a very general remark now. So we looked at this case of, in our case, gamma was equal to, SL to Z inside PSL to R. Oh, what is it? PSL to Z. So this action is not free. So not free action. It does not act freely on H. So it means that the quotient was not smooth, right? So the quotient that we got, H over gamma, the orbit space, turned out to be non-smooth. So the way we approached this problem was, first of all, we found the fundamental domain, right? Right. And in this fundamental domain, so we found this I and rho, which was e to the 2 pi I over 6. 60-degree. These 2 points, so they just we just this gave us a kind of surface with 2 conical singularities. This is pi, so this is pi of I, and this is pi of rho. These are conical singularities. And this point at infinity is a cusp form, a point. So, non-smooth, non-compact. So it's not covered by this story here, actually. But this doesn't mean that this story is not useful. This story is extremely useful because we can construct all compact Riemann surfaces of higher genus by this method. This is this is modular surface. That's what we called it. That's what it's called. So we decided that to do a spectral theory on this, we better just work upstairs and work equivariantly upstairs and then declare what we find here to be related to spectral theory on this. We didn't directly work on that. So it's an orbifold. So.
And so I have a question.
Yes.
So it means that is this what we do to define a Laplacian on an orbifold? Technically, there is no Riemannian metric like at the singularities.
You can talk about Riemannian geometry of orbifolds. There is a theory, but we are not developing that theory, right? So we are not talking. We are morally speaking, we consider this still as a Riemannian manifold of constant curvature, -1, non-compact, but we are aware of that there are these 2 points like this, and also it's non-compact. So we decided to work here and then interpret results as pertaining to this, because this picture, of course, works perfectly well in the case of in this case. Everything is smooth and I didn't give you even one single example, by the way, of a gamma which acts freely and such that the quotient is, for example, a compact, a smooth Riemannian surface. I haven't given you any example of that. So, but there are zillions of examples. So the so-called arithmetic subgroups of these things, they all satisfy these properties. And yeah, this is the theory of Fuchsian groups, and a lot of things are known about them. So, but it's a huge, it's a sea of results over there. So if you go inside the theory of discrete subgroups of this, it's a fascinating world. I mean, there's so much still unknown about these things, spectral theory.
So would it be right to say that if we formally define what a Laplacian is on an orbifold, it would be the same as acting equivalently in the universal cover and then transferring results down?
Yeah, that's
Okay.
that would be, yeah. Although I haven't seen any result, any paper written like that works with orbifolds, and then you see that, yeah, these things don't cause any problems, and at the end you do get the same results as here. So I wouldn't be surprised if some people took up that question and studied this from orbifold point of view. But this is the picture we are looking. And we are going to actually do very, very little today because it's a huge subject. I will give you some references as to what the spectral geometry of modular surface is. It's a huge subject. Okay. Did I answer your question?
Yes, thank you.
Okay, very good. So now, what we want to do? Okay, so well, I mean, okay, Laplacian here. First of all, I mean, this Laplacian, we have the formula for it, minus y2 d2 dx2 plus d2 dy2. Okay, so now to look at things here, so so we are looking at some functions now upstairs. So we're looking phi from H to C, some non-zero function. Such that, of course, it's smooth, such that Laplacian of phi is equal to lambda phi, and such that phi is equivariant, phi of gamma z equal to phi of z, sorry. So this is for all gamma belonging to PSL to Z, or in general, the group that you're looking here, and for all Z belonging to upper half plane. But this is still a crazy problem. I mean, if you just don't impose any boundedness condition, any growth condition at infinity, it can easily, you can more or less easily show that you're going to get a non-discrete spectrum. So one way to get discrete spectrum to put some growth condition, some or L2 conditions. And then the L2 condition that you put here is the following. You just say that integral of absolute value of phi of z squared over x, the mu of z, okay, I'll say the volume G, z is less than infinity. So such functions traditionally has been called mass waveforms because they have been studied by mass. So these are mass waveforms. So he initiated the study of these things as needed for number theory to modular forms. Okay, so what we want to do, very, very limited thing today now. I just present one result, one calculation, and then we just leave it at that, because to do justice to this, you have to start from beginning, do a lot of preparatory work, analytic works in the Eisenstein series, analytic Eisenstein series, and yeah, a lot of other stuff that's needed. So, which, oh, by the way, this was, okay, so, yeah, no, that's fine, this is fine, these are all fine, yeah. Okay, so what is the approach they are taking now? So first of all, change of variable. This is a very important change of perspective in this. So you let lambda equal to s times 1 minus s. Things turn out to be much easier in this parameterization with respect to s rather than lambda. So yeah, so s belongs to C, complex numbers. And right now, actually, even we don't know that lambda has to be real. Even. We don't know that. I mean, because we don't have a nice kind of self-adjointness property, analytic self-adjointness property here for this function. So everything here has to be approached very carefully and patiently. So let's me just okay, so now take such a phi. So certainly phi has this property that phi of z plus 1 is equal to phi of z, right? For all z belonging to upper half plane, because an element of this discrete group, there's a translation by one map, it's there. So this follows from this invariance property in particular. So it means that we can fully expand, and you can just write phi of x plus iy is equal to some. Now the coefficient, so at each level you can fully expand, but then the coefficient depends on y, right? So we get some an of y e to the 2 pi I and x n belongs to z. So this is just periodicity with period 1 of such phi. Now this phi must satisfy this equation also. Now, if you look at Laplacian, I mean this Laplace equation, I mean eigenvalue problem, this side, I mean the eigenvalue problem in this case, it implies that each an, each coefficient an must satisfy so a modified Bessel differential equation. A modified Bessel differential equation. Okay. So once you know that you have the equation, the general solution of those equations in terms of power series expansions are known. So not you know, what I'm saying is that general solutions of modified Bessel. If you know the general solution, so they can be, it implies that this u phi of basically x plus iy, because each an is a linear combination of those two solutions, is of the form c1 y to the s plus c2 y to the 1 minus s. Now we have switched the spectrum from lambda to s times. So we are parameterizing a spectrum in terms of s. These modified things, they have a parameter they define for all complex numbers. So this form plus y half sum an k s minus 1 half. This k is modified Bessel function. N different from 0, we took n equal to 0, this is the part. And then there is a the variable here turns out to be actually 2 pi log y. And then, of course, there is an x component, 2 pi I and x. Okay. Now, this surface, this fundamental domain, I mentioned that it has finite area pi over 3, right? Recall that area of, I mean, this gamma h, I mean, this fundamental domain, or this the modular surface. So this is our modular surface, basically, right? Under this Poincare metric is equal to pi over 3. So this is finite area. So if I have a bounded function, I'm guaranteed that this condition is satisfied. Okay. So let's impose the boundedness on phi.
Sorry, could I clarify what the change of variables is again? I forgot to copy it down.
Oh, the change of variable, what I call change of variable is the following. Let's write lambda in the form of s times 1 minus s. You can always write it.
Okay.
There exists, I mean, for any lambda, there exists an s. The thing is, this differential equation is much more naturally expressed in terms of s rather than lambda. So,
okay,
that's a convenient parameterization. It may have a deeper meaning, but I'm not right now aware of that. So let's impose boundedness condition. On such phi. Then these two terms drop, because if you have such terms, they cannot be bounded. Then it implies that phi of xy, x plus iy rather, is equal to this part. Yes. So let me call this a star, and let me not write it, I put it here, equal to a star. So these are in general mass waveforms for this particular case, and you can further impose the condition that it vanishes at infinity. And with extra condition, phi at infinity equal to 0. So you know, we have discussed At this point equal to 0, this is called the cost form, mass cost form. We get mass cost form. In the spectral parameter S. Yes. Well, the real part of S turns out to be between 1 and 0. So if you now insist on L2 condition, you can actually go on. People have done this actually and calculated the spectrum in this case, and they found a discrete spectrum. Okay, so let me just write it in one word, because I'm not going to get involved into details of this, because that's just really another topic right now. But, so then get with L2 condition imposed, somehow miraculously you get a discrete spectrum for this non-compact space. Get discrete spectrum for this one. So the first few values are I just copied from. So good reference. I mean, for this you can. There was a paper of Sagier, I mentioned Sagier et al. Paper. I think he has another collaborator in this paper, which I keep forgetting. I'm sorry. Paper. So you can read the paper on arXiv. I think it appeared a few years ago, maybe 3 years ago. So, and then there are excellent references in that paper to all this stuff. And they do some beautiful work with this thing. So this is just a starting point. Then they just develop explicit formulas and develop Zeta functions. They find relations between this and periodic geodesics on this and this sort of thing. So they do a lot of stuff with that. So so the spectrum of delta on this quotient modular surface M is, of course, 0 is in the spectrum now, because constant function 1 is L2, because this is finite volume, and delta of 1 is 0. So 0, there's a simple spectrum. And people have calculated these things numerically, 91.141. There are some points, I'm not sure. There is one I remember I wrote, 148. Some digit I forgot. And then it goes on. I believe these numbers have been calculated precisely. I mean, precisely means numerically to 3-4 decimal digits to thousands of, thousands of them have been calculated. And people are interested in these numbers because these numbers somehow is supposed to reflect distribution of eigenvalues of random matrices. Okay, so the spectral distribution here, they should be related. I mean, they seem to be related. Maybe put it like this: seem to be related to random matrix theory. And I don't know what else, but so there is some explanation there. I mean, there are some conjectures that people are working on that. So, but I haven't looked at those issues at all. So I better say nothing. Okay, so So this is one non-compact surface where you get a discrete spectrum. Of course, I mean, you can also, as you know, I mean, get discrete spectrum in quantum mechanics. For example, harmonic oscillator, it's on the line, and its spectrum is discrete. It's not. So I mean, a simple. But I mean, the problem is, in that case, it's not the Laplace operator. It's a perturbation of the Laplace operator that's as discrete spectrum. So let me write it: a simple differential operator on a non-compact manifold with discrete spectrum. Of course, it's the harmonic oscillator, right? H equal to -1/2 d2 dx2 plus 1/2 x squared. You can put x4, x6 here, these coefficients, they all will give you such results. I mean, this, you can imagine this is on R. So this is harmonic oscillator. Quantum harmonic oscillator. I mean, the spectrum of this guy is essentially, if normalization is correct, is going to start from half, and then you go one by one. But the problem is, of course, this is not Laplacian. This is the Laplacian, which has continuous spectrum on R, but we have perturbed the Laplacian by adding a potential. So it's just kind of creating a barrier at infinity. So the particle is almost like confined in some finite area, almost like. So this is a confining potential that creates discrete spectrum. But here, there's no potential. It's just everything is done by the Laplacian itself. It's the negative curvature and other features of this modular surface that creates discrete spectrum. Okay, so anyhow, so I think I'll just drop this at this point, and then I'll make some general remarks about the applications of zeta functions that we had in mind we wanted to do so. Are there any questions? Or?
In a spectral theory, when we have a function which is not a 2, do we call it again an eigenfunction?
Yeah, I mean, it's kind of very. Yeah, I mean, if you are in the context of Hilbert space, you have to stick to the context. But it doesn't mean that it's not a good idea to consider non-L2 eigenvalues or whatever. Yeah, I mean, formal eigenvalues also are useful. So yeah, I mean, these are all kind of. You should keep your eye open about all these things. I mean, and depends what problem wants to tell. Even in quantum mechanics also, they consider situations where you don't have a Hilbert space. You have some space of function which is not a Hilbert space, but it's still useful. It's quite useful to work with that. And then you infer something about the existence of continuous spectrum, different. Yeah, I mean, that's right. So that's another issue. Yeah. All right. So.
What was the name of that paper you referenced before?
Oh, I gave you the name of the author. Just check Zagier and Spectral Geometry archive, and then the paper will come up. I just gave you the name. I don't remember the name of the paper.
Do you know if it's period functions for Moss waveforms? Does that sound familiar?
Yeah, I think that's it. Yeah.
Okay.
It's a two-person author, two authors. Yeah.
Okay, it says here, if this is the paper, Lewis is the only author.
What's it called?
Period functions from Moss waveforms, published in Annals, and the co-author is Lewis. I don't know if that's the paper though.
Yeah. Which journal is it published?
It's published in Annals of
Oh.
Mathematics. It was the first one when I came up when I searched his name in Moss waveforms. So I don't know if it's the one you're thinking of or not. But
It's published in 19. I mean, this was in archive. First appeared in archive 2017. What year you have?
oh, this definitely isn't it. Then this is much
No, that's
earlier.
not
This
it.
is in
No.
2001.
No,
Okay,
no,
I'll keep looking.
that's not. Yeah. It's just look at archive. Just put archive into your search. That would limit the thing. Yeah. Okay. So let me just start. Okay, so yeah. So now the next topic, which is related to what I've been talking about, is we want to sort of look at zeta functions as a bridge between, I mean, kind of, I would say, classical geometry say geodesics, for example, and the spectral geometry. Okay, so let us recall the Riemann zeta function. That's what we did. I mean, kind of most fundamental, most maybe important even zeta function is Riemann zeta function. So we defined it, several times already by two formulas. One was a sum, the other was a product. We defined it to be sum 1 over n to the s, and bigger than or equal to 1. We also defined it by a product, by infinite product over primes. Okay, so we have this, and the fact that these two are equal, this is called Euler product formula, right? This is a very important, very deep observation of Euler. This is called Euler product formula, but nevertheless, we can define it either by right-hand side or by left-hand side, and the quality of these two reflects a very, very deep fact about zeta function and about primes and all these things. So anyhow, so originally this guy is convergent and holomorphic in real part of S bigger than 1, right? That was the first step. And then in the next step, we said that this zeta can be meromorphically extended as meromorphic extension. C with a single pole, which is simple at s equal to 1, with a unique simple pole, unique pole, actually turns out to be simple, at s equal to 1. So this already needs some work. Was not obvious. So this is one thing. And then we said that this function satisfies a functional equation, right? Zeta s. So there's this functional equation. Which was, we proved it essentially using this Jacobi inversion formula, which says Zs equal to Z1 minus S. Where Z is this completed zeta function equal to pi to the power minus S over 2, gamma of S over 2, zeta of S. So this is called completed zeta function. So these 4 steps. Now, what we didn't do was maybe I'll just come up to here. Yeah. What we didn't do was is the following. I mean, really, the application of this zeta function. I mean, okay, so this looks nice and beautiful and kind of hard, some stuff. But what is the real application? The real application of zeta function is to distribution of primes. Okay, so application. This is why people are quite interested in that. I mean, basically, zeta of S to distribution of primes. I mean, more precisely, what is related to distribution of primes is information about zeros of zeta. So let me, first of all, zeros of zeta. So let me put it like this: knowledge on the location. So this is a general principle that I just write, but then it has to be corroborated. It has to be verified. Knowledge on the location of zeros of zeta gives information on the distribution of primes. Okay, so what do I mean by this? I mean the following. So first of all, you know that zeta is not 0 for real part of S bigger than 1. So the first thing to notice is that zeta of S is different from 0 for real part of S bigger than 1. So in the full right half plane, this is non-zero. The reason this is non-zero is this Euler product formula, because these factors, none of them are 0, and theory of infinite product is such that in that case this shows that this is not 0. So it's not just for real line; it's for all complex numbers. For real part of them bigger than 1. Right? So if you are here, then this is never 0. Okay, now that's very good. So, but it looks like, okay, so what is the relevance of this to distribution of primes? So let me tell you now. That by itself doesn't have much in terms, I mean, doesn't have much information in terms of distribution of primes, but just wait a second now. So let's define Ix as, I mean, Gauss, Riemann, Chebyshev, all these people did. Let's define this function to be equal to number of primes less than equal to x. So this is this famous prime counting function, right? So like this was like n of lambda in the spectral geometry, the eigenvalue counting function. So let's look at this. Now, prime number theorem. There was a conjecture first that this pi of x is actually asymptotic to x log x as x goes to infinity. Okay, so this is prime number theorem. This was conjectured for many, many years before it was proved in 1898, I believe, by Hadamard and de la Vallée-Poussin. The method of proof is very interesting. They showed that this follows from the fact that Riemann zeta actually does not vanish on the line s equal to 1. So zeta of s is different from 0 on real part of s equal to 1, because we know that it can be extended anywhere. But what they showed is that if you prove that zeta of s is different from 0 on real part of s is equal to 1, then this follows. Okay? This follows prime number theorem. So PMT. Okay? So, so this was a major thing, but then the thing that there was a kind of very neat proof of this using covariant theory. So alternative approach. So Wiener took all these results and kind of turned it into a huge machine called covariant theory. I mean, alternative. Well, I mean, covariant theory existed, but Wiener did something. Alternative approach. Wiener's covariant theorem, Norbert Wiener's, can be applied in many other situations. The Wiener covariant theorem actually shows by some general method that if you prove that Riemann zeta function is not 0 on the line s equal to 1, then this prime number theorem follows. So that's maybe even more, but I'm not sure right now. So let me just. Okay. Well, so then, but the next step was even more dramatic, and that's what actually Riemann did. So Riemann hypothesis, of course, is that the only non-trivial zeros, all non-trivial zeros, of zeta s are on the critical line. So non-trivial zeros, of course, we're saying because we know that zeta vanishes at negative even integers. We saw that, right? So zeta vanishes at negative even integers. So those are called, yeah, I mean, -2, -4. Those are called trivial zeros. The other zeros, well, here there are no zeros. Here there are no zeros except those trivial zeros. The other zeros, the conjecture is that it's on the line real part of s equal to half. Okay, so but what does this further restriction of location of zeros has to do with distribution of primes? So it is known that this Riemann hypothesis, if it is verified, implies something much, much stronger than this prime number theorem. It implies that pi of x is actually equal to Lx plus O of capital O of x to the power 1/2 plus epsilon for all epsilon positive. Let me explain. So Lx is this logarithmic integral function, which is the integral from 2 to x dt over log t. I mean, I write log, it means really natural log. I mean, log means natural log, it's not base 10. So this is this function. It's a very important function. This function is actually, it's elementary to show that this is asymptotic to this, to x over log x. But it's crucial to replace x over log x by this Lie function in order to write a nice remainder term, which is O of x to the power. You see, this is much stronger than this, right? It tells you exactly what the difference is, what is the nature of the difference. It grows, of course, it grows to infinity, but not faster than x root x plus epsilon x at this point. So this is kind of very strong asymptotic behavior for distribution of primes, provided you can prove Zeta function. So the two lessons that we need to have in mind when you're going to generalize this to other contexts are the following 2 points. First of all, zeros of information about zeros of zeta gives us kind of prime number theorem sort of things, and analogs of Riemann hypothesis gives the best information about distribution of primes. Now, how people try to prove this, because I need a little bit of kind of introduction to that, and then we can give explicit examples. So one possible approach one approach, I should say, I'm not sure this is really possible, but one approach is the so-called Paulia Hilbert approach. So what is Paulia Hilbert approach? I'm not sure if how Hilbert is responsible for this. I'm not sure even they did even any work on that, but there is an idea which is attributed to Paulia and Hilbert. The idea is this: if you can write down a self-adjoint operator on a Hilbert space, if there exists a self-adjoint operator, I mean, this is important, on some Hilbert space H, such that spectrum of this, say H, spectrum of H is related to non-trivial zeros. To non-trivial zeros of zeta. So by related, for example, I mean the following thing. If you, well, I mean, this is over here, right? This is 1/2 plus IT, right? So I mean, so in this, in the following sense, that lambda belongs to a spectrum of H if and only if I would say I lambda plus half belongs to zeros of zeta, for example. Huh? Yes, self-adjoint, because if it is self-adjoint, it means that lambda is real, and then you have real line, and then you just multiply, and then you shift it by half. So, okay, so if you have a self-adjoint, you can formulate it in terms of skew adjoint, and then you don't have to multiply by I, and you can shift it. I mean, that's so the idea is very clear. Then this implies then you get Riemann hypothesis. Why? Well, it's trivial because in a spectral theory you prove that if you have a self-adjoint operator, if it is bounded or unbounded, if technically it's self-adjoint, then its spectrum is real. And spectrum in this case being real, it means that zeros are on the critical line. So this is the approach of so-called attributed to Paulia and Hilbert, and that's one approach people try to construct this operator H and this Hilbert space H by different methods. And so that's one approach. And that's more or less the approach that we're going to apply. So now this approach actually so far did not work. I mean, people are still working on proving the thing in this case, but in some cases this approach worked. So in the case of Selberg zeta functions and also for zeta functions of graphs, it has worked. So, okay, so for Riemann surfaces, and graphs, this has worked. And has given beautiful results on distribution of kind of analogs of prime in that case. So this is due to Selberg and Ihara and extensions. So in other words, in these sort of geometric situations, there is a zeta function. I'll also discuss a little bit of that last lecture. And if you construct this operator H and find a relation between the two, then you can prove a lot of interesting results about the type of primes that you're considering in that case. So maybe I should stop, and if there are any questions, because I have 15 minutes still, I can continue. Any questions? Or? Okay, so now we are going to kind of implement this idea in the cases that's been known, namely for Ihara zeta function and for Selberg zeta functions. Okay, so Ihara.
I have a quick question.
Function of graphs. Yeah.
how much of the Ihara zeta function stuff are you going to talk about? Because that was going to be the basis of my presentation.
Oh, this? Oh, I'm not. Well, I will discuss. Are you worried about it?
No, it's yeah.
Don't worry. I will. This will be a very good introduction for your presentation. No worries.
Okay, perfect. All right, thanks.
So let me just give you a kind of. Yeah, I think there are at least two ways. Which one are you doing? You are doing for directed graphs or non-directed graphs?
I was going to do for non-directed graphs, but I could do either. So
yeah, because I think there is so much you can do still. So that's
okay.
But let me just. So this is the philosophy here. So now let me just do this. So of graphs. Okay. So what we're going to do now is the following. So take a finite graph. The finite graph. So this means that well, V is a set of vertices and E the set of edges. So this is less than infinite. Number of points of V, number of points of edges, number of edges also is less than infinite. Okay. So okay, so for a graph, let me define a cycle in G is the following. So a cycle in G is some sequence of vertices like V0, V1, V2, Vn, such that V0, V1, V2, V1, V2, and so on, they are vertices of edges. So like this. So instead of writing it, let me just give you, so you start from some vertex V0, you go V1, V2, V3, V4, right? And you go back, but now the thing is, there is no kind of backtracking. Okay, so you're not allowed to write V0, V1, then V1, V0, and they go on from there again. So with no backtracking, in other words, with no backtracking. Okay, so this is a cycle. So it's kind of loop that kind of closes the point that is stuff. Now we are.
Is this independent of an edge that connects two vertices? Because you could have more than one edge connecting the same two vertices, right?
Yeah, I'm going to actually say soon that there's going to be at most one edge connecting two vertices. Yeah.
Oh, okay, good.
I'm going to specify those things. Yeah, this is a good point. This really depends on that. So okay. So now second thing is you just say a primitive cycle. So I define three concepts and you see what's going on. It's a primitive cycle. So primitive cycle is a cycle that's not multiple of another cycle. So not a multiple. I mean, these things can be rigorously defined, but it's waste of time to do that because it's very clear what I mean. Primitive cycle, not a multiple of another cycle. I mean, for example, in this case, if you have V0, V1, V2, I mean, if you write V0, V1, V2, and then V0, V1, V2, obviously this is twice the original cycle. So we just throw that away. We don't consider a non-primitive cycle. We just look at primitive cycles, okay? So geometrically, that's it. But if you want to kind of be very formal, you can say that a prime is equivalence class of primitive cycles. So what is a prime? That's equivalence class of a cycle, I mean of a primitive cycle. So what does equivalence class means? Well, I mean, this presentation is not unique. I can start from V1. And then geometrically, you get the same thing. It looks like it's kind of reparameterization. That's, I mean, e.g., I mean, V0, V1, V2, I consider it as the same as V1, V2, V0, etc. So that's also clear, right? Okay, now the conditions are, so Jeremy had this question, good point. So conditions on G assume that, well, each two vertices, there exists at most one edge. Some conditions at most one edge between any two vertices. Right. Also, no loops, I mean, at the vertex. I want to take loops at the vertex. And no dangling vertices. I just say dangling vertices. I mean, by dangling vertices, I mean a one-valency vertex. So something like this that ends here and doesn't go anywhere, no, this is not okay. So this is valency equal to 1, vertices is not okay. So we just delete those possibilities. Otherwise, we just take any finite graph. And then this Ihara's, or this is a generalization, really was done after Ihara, a long time after. So the thing is now is the following zeta function. So let me. So did I cover much of your presentation already?
No, not at all.
Okay. Okay.
This will help.
Okay. Very good. So now, so Ihara zeta function. So I would say, let's call it zeta G of one notation is U. Some people put T here, some people put Z. Let's put U. I mean, this is like one good notation. Is an infinite product, 1 minus P to the power S. So let me put it like this. U to the power L of P minus 1 over P belong to P. So P is a set of primes in G. What primes really means closed geodesics, right? In disguise, but we call it prime by analogy with prime numbers. So we call them primes. So what is L of P? Okay, LOP is length of this geodesic. It's just its length. Put the length of prime. In this case, it's 3, for example, and so on. Well, you're supposed to be a complex parameter in C. Okay, but I mean, if you look at it, you notice that this is, of course, very much like the one definition of Euler, the Riemann Zeta function. The only difference, if you compare this, we have pi minus p to the minus s minus 1. So it looks like that you're saying u to the ls is equal to p to the power minus s. That's the connection. So yeah, okay, right. So length, if you take log on both sides, you take that L of s log u is equal to minus s log p, and it looks like that really log of p is related to this parameter L of s by this kind of. So it's so the variable has changed. It's a different presentation. This we can write it in this form also. I can write this in the denominator, writing as an exponential and all that. But they have their own virtues. There's a virtue here to write it like this, which is kind of important. So that's now one thing to notice is that this P could very well be an infinite set. It's countable, but it's infinite set. So let me just write it. So this is a warning. P can be infinite. Right. So the convergence of this thing is not clear at all. Where is it convergent is not clear at all. So for right now, we will make it clear soon, but this is not so convergence disk is not clear. This is infinite product in general. That's what I'm saying. So, okay, let's look at one simple example at least. One thing I didn't say is that also for each kind of loop, we should also consider the loop in the other direction as a distinct loop. So every term here appears twice, basically. This is what we did also for the case of circle in the last lecture. You remember? We took one geodesic, primitive geodesic in this direction, other one in the other direction. Right? So that's what. So also each loop is tracked in two ways. One is like going in this direction, same loop, geometric loop, you can go in this direction. We take them this. So let me give one example and then we are done. And then, I'll tell you what is known, a little bit of things that is known. So example, the simplest example is just cycle graph. Something like this, right? So cycle graph. So here in this case, there is only one loop, just one loop, but we have to count it twice, right? And what is the length of this loop? mean, one prime, in other words, what is the length of this prime? Well, let's assume there are n edges, which are n vertices, right? So let's this be equal to n. So that's kind of n cycle. Okay, so then the zeta function in this case, this is g. So zeta g u is equal to 1 minus basically un power minus 2. But so for typically, I mean, you can have infinite set of primes or geodesics in this case. So we want to obtain information about number of primes in such graphs. What is the distribution of primes? So prime graph theorem, something like that, if you can call it. And we also want to see if there is a Riemann hypothesis can be established for these things, plus Riemann hypothesis for these Ihara Zeta functions. Not for all G's, for some G's only, because only for some G's functional equation can be established, and that's crucial. So these are the things that we can, but I mean, some of these things will be covered by Nathan. So I can stop then talking about these things and then move to other aspects, which is parallel to this, well, much more complicated, which is Hilbert Zeta function. So we can go to Riemann surfaces. So the idea is that, yeah, a graph is a kind of toy model of a Riemann surface, after all. This is kind of one of the visions that will emerge. So I will stop here before my